In today's lecture, we will be looking at some example problems on using the method of work and energy, but I will start with explaining the concept of the term called power. Now, in physics, power has a specific meaning, and what we mean by power is the rate at which work is done. Now, work, as we have seen, is done by a particular force. So, power is the rate at which work is done, and what we know is that the amount of work done if a force F, if under the force F, influence of this force a particle moves a displacement delta r, then the work done in this displacement is given as F dotted with dr. Now, if we look at the rate at which the work is done, that will be delta W by delta T, and this we can write it as F dotted with delta R by delta T, and this will be nothing but F dotted with V if we are talking of when a force is being applied on a particle. So, this is what we term as power, and sometimes this is also called the instantaneous power, because at time t when the force F is being applied and the velocity of the particle is V, then because of this force F, the power will be F dotted with V, where V is the velocity of the particle. Now, so here V is the instantaneous velocity of the particle. If we look at the units of power, well, first we realize that like work done, power is also a scalar quantity, and if we look at the, to get the units of power, we first look at the dimensions of power, and the dimensions of power will be m times L2 t to the power of minus 2. These were the dimensions of work done, and then for power we have to divide it by 1 more t. So, this becomes equal to m times L to the power of 2 t to the power of minus 3, and if we look at in terms of SI units, this will be joules per second, and this is called as watt. So, 1 watt is equal to 1 joule per second, and often what you will find is you also will see a term called horsepower, which is used for power, and this is 1 horsepower is equal to 746 watts. Now, this comes from British units, so we just keep it because it is often very much used. Now, one of the places where we see the use of power is when you get your electricity bill, and in fact the electricity consumption, this is in terms of energy and not in terms of energy per unit time. So, what we have is the what we call as 1 unit of electricity, which is what you see when you get your bills at home. This is equal to 1 kilowatt hour, which means if 1000 watts of power are consumed for 1 hour, that is what gives us 1 unit of electricity. And so, one can see this, if we look at this unit 1 kilowatt hour, 1 kilowatt hour, this is 1 unit of electricity, this is equal to 10 to the power of 3 watts into 1 hour, which is 3600 seconds. So, this will be equal to 3.6 into 10 to the power of 6 joules. That is the amount of energy used when we use 1 unit of electricity. And so, you can then now compare how much, you can now calculate how much energy is used when a 100 watt bulb is lighted for 1 hour, etc., and how many units it will mean. So, this is in brief a definition of power. Now, actually the power in a fundamental sense is used when we try to use this law of conservation of energy in a differential form. but for our purposes we will not use it, but one can differentiate the work kinetic energy equation with respect to time, and then when we differentiate work we will get power. On the right hand side, other side, we will get the change in kinetic energy. When you differentiate that with respect to time, that will give you dk by dt, or the rate of change of kinetic energy by time. So, we have seen the energy methods as a whole, and let us try to sum up how energy method help us in problem solving. So, let us see problem solving using energy methods, energy method I should say. Now, energy method is useful, and you will find it's often simpler to solve problems using energy method, which I will explain why. It is useful when we have two configurations or two positions of a body. By two positions, so for example, I have a block which is travelling on the incline, it is at position 1, it travels up to position 2. So, or it could be something travelling, a block moving on a circular track, this is position 1, when it moves at the topmost point, this is position 2. Of course, there could be many more positions, and we could apply energy method between any two positions. And what will happen is that we will often need to find either the force, the velocity, or the position at one of the two configurations. In general, what you will find is that when we use energy methods, we will not be finding accelerations, because when we see the energy method, what we are doing is we are taking Newton's law, which is F is equal to ma, and we are integrating this with respect to position, with respect to dr. We take F dot dr, that is what gives us work done, and on the other side we get that is equal to the change in kinetic energy. So, the work energy method is actually in some sense an integrated form of Newton's law. With Newton's law, when you apply second law, you can get acceleration at each configuration, not at 1 or 2. But when we integrate this, then and we apply the integrated form starting from position 1 to position 2, that is where the work energy method turns out to be useful. Now, what are the advantages, we will just see, but when we start any problem where we want to use work energy method, or we will be able to, when you start, you want to know whether you can use the work energy method, will it be useful or not, or should we use Newton's law. So, the first thing which you do is that you physically, and sometimes it may not be physically, just or mentally, you draw the free body diagram of the particle. So, the particle which is moving, the block which is moving, you draw the free body diagram. And when you draw the free body diagram, what you will do is you will observe the forces acting on the particle. This is what a free body diagram does. It shows you all the forces acting on the particle. So, mentally you draw the free body diagram, or physically you draw the free body diagram. So, for example, when I say this block is moving up the incline, I draw the free body diagram of the block. So, then what I will have is, if the block is moving up the incline, there is a weight mg, there is a normal reaction, and then there is a friction force, and possibly because the block is moving up, there has to be some sort of an external force which is pushing it up. So, we mentally draw the free body diagram, if not physically, at least have the picture of this free body diagram. Now, the advantage of the work energy method is that if we use the work energy principle, then we know the path of the particle. Any force which is perpendicular to the path of the particle does not contribute to the work done by external forces on the particle. So, this is the first simplification which comes. Let us look at this example. In this case, this particle is moving up along the x direction. The normal reaction n is always perpendicular to x direction. So, if we use the work energy method in this problem, we do not have to bother about n, because we know the work done by n will always be 0. In this problem, there will be work done by mg, work done by friction, work done by force F, which have to be accounted for, but work done by n will not be there. So, this is where one simplification comes, that when we draw the free body diagram, we will be able to realize that some of the forces do not do any work, and this particularly will become more useful when we have more than one particles which are connected, because then what we will find is that there are some interconnections between the two bodies, and these interconnecting forces will do work on body 1 as well as body 2, but when we look at body 1 and 2 together as a system, then these forces will not do any work. And so, the workless forces makes our job easier. Now, what is the work energy principle? Work energy principle says that change in kinetic energy is equal to work done by all external forces. So, the body moves from configuration 1 to configuration 2, then we calculate the work done by all external forces as the body moves from 1 to 2, and this sum of all the work done is equal to the change in kinetic energy, which means this is equal to kinetic energy at state 2 minus kinetic energy at state 1. Now, the second simplification which comes is that when we talk of work done by all external forces, what we have seen is that there are some external forces where or whose work done can be written as minus the change in potential energy. We have seen these forces in the last class. So, for some of the external forces, the work done is equal to minus the change, and we use the symbol V. So, let us say there is a force 1 which has a potential energy, force 2 for which a potential energy can be defined, then the work done by those forces can be written as minus the change in potential energy. And these forces we call them as conservative forces. So, if we have any conservative forces in the system, the work done by these forces will be given as minus the change in potential energy. Now, the usefulness of this conservative forces is that the work done by conservative forces, it only depends on state 1 and state 2, and it does not depend on the path taken between 1 and 2. So, therefore, if we take the work, so what we can write is, let us come back to the work energy equation, delta K, we write it as work done by conservative forces plus work done by non-conservative forces. And the work done by conservative forces, this can be written as minus delta V. So, this gives us delta K plus delta V is equal to the work done by non-conservative forces. So, this is the simplification which we get in case if there are no non-conservative forces acting in the on the particle, then change in kinetic energy plus change in potential energy is equal to 0, and so we can find the potential energy or the kinetic energy at one of the two configurations, and depending on whatever the unknown is, we will be able to solve our problems. So, this is how one can then use work energy methods for to help in problem solving. Now, one thing we realize is, and this you can see as a limitation of the work energy principle, is that what we will be able to get at configuration 1 or configuration 2 we will be able to get the speed at 1 or the speed at 2. This we call as V1 or V2. Assuming that one of them is unknown, we will be able to get the speed, but we will not get the velocity vector. Of course, if the problem is of one dimensional motion, then this also becomes, you will get to know the velocity vector, because velocity is along that line only. But in case of two dimensional motion, you will be only able to get the speed. So, does it mean that the information given to us which we get from speed is a useless information as far as accelerations go? Well, the answer is no. Suppose if a particle is moving along a curved path, then what we know is at any position, let us say 1. So, if this is position 1, the normal component of acceleration is equal to v square upon r, where v is the speed of the particle and r is the radius of curvature. So, if this is a circular path, then r will be the radius of the circle, and so a n is equal to v square upon r. So, the speed is what we may get from energy methods, but once we know the speed, then we know the normal component of the acceleration is equal to v square upon r. And so, if we know the path, generally in a lot of problems it will be a circular path, then it will be just v square divided, v here is of course the speed. So, speed square divided by r will give us the normal acceleration. So, we will get this value of v from energy methods by using principle of energy, and then we can use this to have the normal component of acceleration, and using normal component of acceleration we may also get the normal component of the force, and this will come from Newton's second law. So, having seen this, now let us look at some of the problems which we can solve using work energy principle. Let me just go back to this particular example which we talked of, when we said we use, if we want to use work energy principle to solve, to look at the motion of the block from 1 to 2, then what we realize is there are 4 forces acting: normal reaction, weight, friction, and the force F which is being applied on the block, which is pushing it up on the incline. Now, here what will happen is you realize the work done by gravity, this we can calculate by minus the change in potential energy, because for gravity, which is a constant force, the acceleration is constant. We have defined the potential energy is mg times the height, where we choose any reference datum, choose that as 0. Work done by n is 0, and the work done by friction force and capital F will have to be calculated, and if we have to find that, we may have to use Newton's second law to find these things. So, this is a sort of brief description of how this can be used. Now, let us come to specific problems. So, let us look at example 1. A block of mass 5 kg is fired up a 30-degree incline with a speed v0 is equal to 5 meters per second. It travels a distance d is equal to 2 meters up the incline. It comes to rest for a moment and then slides back to the bottom, and we want to find the velocity of the block when it comes down at its starting position. Now, here one thing what is given to us is since the block is starting with this thing, it travels only a distance up to 2 meters and then it starts to come down. So, here let us first look at the friction force between the block and the ground, and we will assume this friction force is not equal to 0. It is not given in the problem, so we will start by assuming that the friction force is there, it is not equal to 0. So, if we mentally or physically draw the free body diagram of this block. So, the picture is something like this block is here, it is given, it starts, it is given a push, we do not maintain the force on it, we just give it a push and leave it, and because of this push the velocity is equal to 5 meters per second. It travels a distance d which is equal to 2 meter, it goes up the ramp and this angle is given to be 30 degrees, and so and after that what we want to find is it stops there and then it comes down, and when it comes down, when it comes back to this position, we wish to find the speed, the velocity of the block. So, let us when we look at this, when I draw the free body diagram of the block, I have when it is moving up. So, let us look at the block moving up, there is normal reaction, there is weight and there is a friction force. These are the only 3 forces acting on the block. So, external forces are friction F, 2 the weight mg which is acting vertically down, and 3 the normal reaction. Now, friction force, because the block is sliding, this will be equal to mu k times n. It is a case of sliding friction. So, there is relative motion. So, friction is equal to mu k times n. Now, when we do our this thing, we look at it, n is equal to mg cos theta, that is the, if I take, if let me call this as the x direction, let me call this as the y direction. So, this is comes from sum of the forces in the y direction is equal to 0, because there is no acceleration, and if we look at the x direction, then we will get in the x direction I will get the force is minus mg sin theta minus f is equal to mass times acceleration in the x direction, and because both of these are negative, we realize acceleration in the x direction is negative. So, now one can solve this here, but what is given to us? We are given the distance of 2 meters. So, if we solve, if we try to start solving the problem in this method, we can solve the problem, but we will have to first find acceleration related to the distance d and then solve it. But one thing we realize when we write these equations is, because n is equal to mg cos theta and none of this changes and friction is equal to mu n. So, that means the friction force is a constant force, it is not changing as the particle is moving up the block. Well, when it moves down, it will be a separate story, the friction will again be equal to mu k n, but its direction will change. Right now, it is in the minus x direction when the block is moving up. So, what we do is, instead of solving this equation, finding the acceleration and then relating it to distance d, we use the work energy method. And when we use the work energy method, let us call the starting point as 1 and the point where the block stops, we call this point as the final position. So, now work energy method tells us delta K plus delta V is equal to work done by non-conservative forces. So, let us start to see when we look at our external forces, this is why you need to draw the free body diagram. As I said, it may be a mental exercise, not a physical drawing of the free body diagram. We see there are 3 forces. The work done by N, so when we come to this, the work done by N is equal to 0. The work done by mg, this will come in the potential energy due to gravity, and the work done by friction is what will come in the work done by non-conservative forces. So, now to calculate these terms, delta K is equal to K2 minus K1. Now, K2 is equal to half m times 0 square because the block is stopped at point 2, K1 is minus half m V0 square, where V0 is given to us, it is given as 5 meters per second. So, we know K2 minus K1. Change in potential energy, this is equal to V2 minus V1. Let us take the highest position. So, this is the block, this distance it moves is d, this angle is theta. So, we take this highest position, let us take the potential energy at the starting position to be 0. So, V1 we take it as 0, V2 will be the height of this point from with respect to this. So, this height will be d sin theta. So, V2 will be equal to mg times d sin theta. So, what we have is V2 minus V1, this is mg d sin theta minus 0. So, write each of these terms in one term separately. Each of these terms is quite easy. When we look at the full problem, the problem may look complex, but we divide it into parts, write each of these parts, and each of these parts delta K is very simple. Delta K at 2 is equal to 0, K at 1 is half m V0 square. Similarly, potential energy when we come to it, V2 is equal to mg d sin theta, V1 is equal to 0. Now, work done by non-conservative forces. The friction force is acting in this direction, the block is moving in the upward direction. So, work done by friction can be written as minus of F times d, because friction as we have seen is a constant force. So, therefore, this will be minus F times d, and because these two are in opposite direction, we get the minus sign. So, now once we do this, then we combine everything, what we get is minus half m V0 square plus mg times d sin theta is equal to minus F times d, and from here what we will get is F is equal to m V0 square by 2d minus mg sin theta. So, we get the value of friction force. Now, to find this friction force, we know if the block has to move up, has to be always positive, and this will give us the condition on V0 for this block to move up, or up till what height can it go. Now, after that what we have is, let us look at the, what we have to find is when the block comes down, the speed at its starting point. So, what we will do is, now let us call this position when it returns to the starting point, we call this as 3. Now, physically 1 and 3 are the same point, but what has happened is the block starts from 1, moves up to 2, and after that it is coming back down and it comes back to 3. So, what we can do is, let us apply the work energy principle between 1 and 3. Now, what we will exploit is that friction force has the same magnitude. We have seen this, that magnitude of friction force is equal to mu k n, and whether the particle is moving up or moving down, n is equal to mg cos theta. So, magnitude of friction force is equal to mg cos theta. But what happens is, when the particle moves up, then friction force is in the downward direction, the particle is moving up. So, this is when the particle moves from 1 to 2, and when the particle moves from 2 to 3, it is coming down. So, now the friction force is in this direction and this is the displacement. So, once again the work done by friction from 2 to 3 will be equal to minus F times d, and the work done by friction during its movement from 1 to 2 will be minus F times d. So, that means when the particle moves from 1 to 3, the work done by friction is equal to minus F d plus minus F d, which is equal to minus 2 times F d. And we have our principle delta k plus delta v is equal to work done by friction, and this is now on the entire journey from 1 to 3. Delta k will be equal to half m v 3 square minus half m v 0 square, because k 3 is half m v 3 square. This v 3 is the unknown we want to find out, v 0 is given to us. Now, what about delta v? What is potential energy at 3 and potential energy at 1? Both of them are equal to 0, because the particle is at the same location where the datum we have taken as 0. So, therefore, from here we straight away get half m v 3 square minus v 0 square is equal to minus 2 f times d, and f we have calculated earlier. So, now we can put everything and we will get our answer, and when we work this out we get v 3 is equal to 3.77 meters per second. And we realize the particle comes back with a slower speed, because there is work done against friction which is not restorable, we do not get it back. The work done by gravity is restored back in form of kinetic energy, and that is why it is a conservative force, but work done by friction is not. And sometimes here you may see books will say that any constant force we can express a potential energy with respect to that. We can write an expression for potential energy. Here in this example we see friction, the magnitude is constant, but still it cannot be expressed as a potential energy because its direction changes. So, therefore, the work done by friction cannot be restored back once the particle comes down, we do not get it back in the kinetic energy, and that is one thing which will happen with all non-conservative forces. Okay. Now, also here one can possibly, we know the value of friction, so we can work out what should be the value of mu. Mu k is not given in the problem. So, if you are asked to find the value of mu k, then you can find that out. You know the friction, and the F is equal to mu k times n is equal to mu k times mg cos theta. We have worked out the value of F, so you can find mu k. And the other thing which we realize is, because the block is falling down, that means mu k has to be greater than tangent theta, otherwise the block will stay there only. Now, let us look at another class of problems here, and this is where we use work energy principle quite effectively, and this is motion in a vertical circle. Two types of problems are very common. One is we have a block or a particle which is moving in a circular path, and here by saying it is a vertical circle means gravity is acting vertically downward. It is something like a ring which is kept vertical, and on that block or particle or an insect is moving on the ring. The second case of this is a case of a particle tied to a string which is almost weightless, and then the particle is performing a circular motion. So, this is like a pendulum. In a pendulum we give a small oscillation, so it keeps on oscillating, but here we do not restrict to a small oscillation. Let us say at this bottom point it has a velocity v. Does it complete the circle? Does it oscillate? What happens to it? What should be the value of v is all what we are going to analyze now. So, this is the second case is a mass m tied to a string of length L in a width. So, let us write the second case fully. So, I have a mass m tied to a string of length L and is rotated in a vertical circle with the center of circle being fixed to the other end of the string. So, this is a string of length L or radius length r, that will be the radius of the circle, and this block is moving. Now, in both these cases if we draw the free body diagram of the particle, let us say for this one I draw the free body diagram of the block, what I will see is that there will be a weight W, and when the particle is here there is a normal reaction N. Similarly, when I and then of course we will assume this is a frictionless path, otherwise there will be a force of friction also. Similarly, in this case of a string, what we will have is, if I draw the free body diagram of this mass m, we have the weight mg acting downwards and a string applies a tension force which is equal to T. Now, this is when the particle is at the bottom. What happens when the particle is at the top? So, assuming it undergoes the full circle, when it is at the top, what you will see is, if I draw the free body diagram, the weight will be acting here, and if I look at the normal reaction, then if the particle has to maintain contact, the normal reaction has to act downwards here, because the particle will exert an upward force on the circular block. So, the weight on the particle will be N downwards here, and in this case also if we look at the tension T, the string has to pull the particle down, and that force we will call as T. Of course, maybe I should call it T2, call it N2, because these will not be the same. The weight will be the same, but the tensions will be different. So, this is how we draw, if we draw the free body diagram, we will get pictures like this. Now, when we analyze this, once again this is a mental picture we have to make in mind when we analyze the whole motion. We may not draw the free body diagrams, but mentally we will have to keep this in mind. Now, one of the things which we ask in these problems is often, what is the minimum velocity which the particle should have at the bottom, so that it can execute the full circle. Now, what do we mean by the condition that it can execute the full circle? And for that, what is critical is the velocity at the top point. And to get that velocity at the top point, what will be the condition? How much should be the velocity at the top point, so that it is just able to complete this circle? And the condition for completing the circle will not come from velocity, it first has to come from the normal reaction or the tension T. If the particle has to complete the circle, then normal reaction N2 has to be just positive. That means either this N2 has to be there and the limiting condition will give us N2 is equal to 0. And similarly, the limiting condition for the particle for this pendulum to reach the top part and come back will be that the tension at this point will just be 0. It has to be positive for this, that means it has to be downwards positive as shown for this to be able to complete the circle. So, the limiting condition will be T2 is equal to 0 or N2 is equal to 0, not V2 is equal to 0 in these cases, because what will happen is the place at which V2 becomes 0 will not be some before V2 becomes 0, what you will find is the tension somewhere will become 0 before V2 becomes 0. And once the tension becomes 0, then the string which is carrying this, once this tension is 0, the particle will just fall freely from that position. And similarly here, once normal reaction becomes 0, then the particle will just lose contact. So, if we want the particle to travel the full circle at the top position, that is where the normal reaction or the tension must be 0. So, once we understand this, then actually what we want to find is, we want to find two conditions. We want to find the minimum velocity at the top. So, the particle can rotate in a full circle, and if that is so, then we want to find the minimum velocity at bottom for A to happen. And typically the problems will say in effect you have to find the velocity at the bottom so that it can encounter the full circle. So, find, the problem will not give you part A, it will just say find V at the bottom so that the particle undergoes a full circle motion. So, doing this is quite straightforward, as we said. If I to find the velocity at the top, so this is the circle. If I draw the free body diagram here, as I have said, we have mg and then we have this tension T which is acting. These are the two forces acting at the top, and so we get mg plus T. This is equal to total forces in the radial direction, and this must be equal to m times the velocity at the top divided by r, and r in this case is nothing but the length of the string. So, m times v top square upon L. And so, now the condition to complete circular loop is that T must be greater than or equal to 0. So, here what we have is T is equal to, from here what we get is m times v top square by L minus mg, and so T greater than or equal to 0. When we put this in, this will imply that v top square is greater than or equal to L times g. So, that means minimum velocity at the top must be equal to square root of L times g or square root of r times g, where r is the radius of the circular loop. Now, to find the velocity at the bottom, we use work energy principle, with 1 being the top and 2 being the bottom. So, K2 is equal to half m Vb square, K1 is equal to half m Vt square, and which will be equal to half m Vt square will be equal to L times g. Okay. And then what we see is the only forces acting as the particle is moving. Now, as the particle moves, when it is in a general position, we have the weight mg acting, we have this tension, and we have the normal reaction, and or tension or the normal reaction which will be acting, that is it. So, therefore, the work done by T or N, this will be equal to 0. So, delta K plus delta V is equal to 0. Then we have V 2 is equal to mg times 2L or mg times 2R, and V 1 is equal to 0. So, we have taken the datum as the bottom. So, with respect to that, the vertical height of the top point is 2R. So, this is what we have for V 2 and V 1, and delta K plus delta V is equal to 0. So, this implies, this gives us half m V b square minus V t square minus mg times 2L is equal to 0. So, we get velocity at the bottom. Simplify this, you will get it as equal to root of 5 g L. So, now one thing what we realize is, if you look at this motion, this is not a uniform circular motion. Why is it not uniform? Because the velocity is changing. So, that means the speed is not constant throughout. So, we cannot use formulas for uniform circular motion, it is changing. Also, what we realize in this problem is that the tension T is changing with position. Tension T or the normal reaction N, depending on the class of problem, will be equivalent, they change with position. But because we are using the work energy formulation, the work done by T, work done by N is equal to 0. So, we do not have to bother what is the value of T at each location, and this is the sort of the power of the work energy principle. Otherwise, if we were to do Newton's law at each point, then we would have had to find T at each point, and we would not have been able to work out things so easily. But what we can do is, if we know velocity at any location, now this we can find even at any theta, that means at any angular location we can find the velocity. How can we find this? By work energy principle. We will use just for this, of course, we will need to know velocity at one location, and then we can find velocity at any location on the circle. We use the work energy principle. So, simply using this we can get the velocity at any location theta, and once we know that, then we can draw a free body diagram and use Newton's second law along the r direction to get the value of T or N at that theta. Because what will happen is, because this is circular motion, so along the r direction toward the center, the acceleration will be mv square upon r, and v is the speed. So, at any location, actually I had used velocity, I should have used here speed. Speed at any location can be found out, and so once we find the speed, then we can find the we use this and we can find mv square by r, we can use that to find T or N. So, now let us beat this, try to find some more things from this problem. We have this string, a mass of m, mass m being tied here, and what we want to find is what is the speed at O, so that the mass m just reaches A, and then what we have is half m v 0 square minus v a square plus 0 minus m g L is equal to 0. Now, this I have written it directly, this change in kinetic energy, change in potential energy, this is 0.1, this is 0.2. So, at point 2 the potential energy, if I take it as 0, then the potential energy here will be minus mgl. So, this is how I have taken the datum at point A. So, because this point is down, so minus mgl is the potential energy at position this is the potential energy here, potential energy at A has been taken as 0. So, from there what we can get is velocity at 0 is equal to square root of 2 gl. Now, what we have seen is that if what we saw here was if velocity at the bottom was root 5 gl, then this pendulum completes the full circle. When the velocity is root 2 gl, then it just reaches A, after that it cannot move, so then it starts to come down. So, if the velocity at the bottom is equal to root 2 gl, then it oscillates in a semicircle about point O. If the velocity is less than at bottom is less than root 2 gl, then it will oscillate, but it will not be able to go up to A, it will be able to go up to some intermediate point B. So, it will oscillate with some angular oscillation where this angle theta will be less than 90. The limiting case will come when velocity V0 at the bottom is root 2 gl, then it will be able to go up to A. And when velocity at bottom here, so that means if V0 is less than root 2 gl, the particle, the pendulum oscillates about O, and if or less than or equal to root 2 gl, if V0 is greater than root 5 gl, then the pendulum undergoes a full circle motion. Now, what happens if V0 lies between root 2 gl and root 5 gl? So, if V0 lies between these two values, so the particle which let us say it starts from velocity O, it moves here. Because the velocity is greater than root 2 gl, it will go past the point A. I am just showing this full circle, but then what will happen is, depending on the magnitude of VO, somewhere here at whatever this angle theta is, the particle will encounter a position, encounter t is equal to 0, and at that point it leaves the circular path. It will leave the circular path and then it will move like a projectile under influence of gravity, because then the string will fold, tension will be 0. So, once it leaves the circular path, it will move like a projectile and it will move. So, once t is 0, it will moves like a projectile in a parabolic path. So, this is how one can solve these problems. The angle theta at which the particle leaves can be found out, and in fact after that, because this particle is moving like a projectile, so then you can apply the equations of the projectile to find the height the particle will take with respect to this position, add that to the initial height, that will give you the final height which will be attained by this particle when it is starting from 0 with a velocity between root 2 gl and root 5 gl. So, this is how one can solve such problems. Now, in some other problems you may find springs being connected to the particle. If a spring is connected, then the only, so let us just look at this. If a spring is connected to a particle, the only change which will come is in the potential energy, and potential energy is equal to half k delta square, where delta is the compression or the extension of the spring. So, rest all stays the same. You will have a new force called the spring force, and we will have the potential energy. In the potential energy term, we will add the potential energy due to the spring force, which will be half k delta square. And other terms, if there is a gravity is changing place, so then you have to also account for change in gravity, and sum of kinetic, sum of change of kinetic delta k plus delta v, sum of these must be equal to work done by non-conservative forces. Non-conservative forces typically will be forces like friction or a constant force F being applied in a problem. So, with this we have seen some examples in energy motion. In the next class, we will take up the principle of conservation of momentum and conservation of angular momentum, how they come from Newton's second law for a single particle. Thank you.